And then layer 4 is where the TCP/IP stack runs.
Right, we're just in the network layer at this point, so. Yeah, once we have communicated. And we received the packet. Onto the wire. We strip off. Okay, let me throw this one out. What is it called when we strip off our layer 2 header? Somebody besides William, I know William knows the answer. Talking about stripping in class, and no one wants to input.
This is not the weekend. This is not the weekend. We are talking about.
Oh, I couldn't resist. I want to make you guys laugh. Okay, so no,
The encapsulation.
yeah, de-encapsulation. When we take that header and we strip it off, right? And that is de-encapsulation. So if you need to remember, think about and remember this, it goes back to what I said, put on your packet suit. Okay. So when your packet, if you're going through a network, just sometimes maybe even envision what would I have to do to go through a sewer pipe. I want to wrap myself up. I don't want to get nasty. All right. I want to put something on that protects me. I can get in the pipe, and then when I get to the other end, I got to take that part off, and I'm all clean inside, right? I just de-encapsulated myself. And I think about that movie Inner Space.
Or it's like shipping. It's like shipping a package.
Yeah, shipping a package. You take that packet, take that outer box off, and whatever's inside is the payload. So when we take that layer 2 header off, we're left with this particular thing, an IPv4 packet. And we actually looked at all this really closely yesterday. We looked at IPv4. I say yesterday, but it was Thursday. But I just want to go over it again because there's a lot of information in that slide. So how many bytes does that represent from left to right? Yeah. 4. Yeah, 4 bytes. Does everybody see that? How that byte, where those byte boundaries are and why they're there? Let me make that bigger.
So it's a 4 byte wide, 40 byte long packet.
Yeah. 4 bytes, 6 times 1, 2, 3, 4, 5, 6, 36, 2, 24. So when we look at this, and so this is that other part of when we looked at hexadecimal. I don't have to represent each piece of information that I want to carry into a full byte. I don't have to carry that out. I can do it in half bytes. So I can always represent portions of numbers. And that's kind of what you're seeing here is that this version and traffic class, they're split. And it makes up 1 byte. And these are our bytes that make up our IP addresses. So right here, let me go over to my notepad. Right here at this level is our first byte, our second byte, our third byte, and our fourth byte. These are called octets. And they're called octets because they have 8 bits. So these 32 ones here, or 32 bits, represent my IPv4 source address. And it would basically fill out this packet header if it was all ones or all Fs.
And that would be a broadcast address.
It would be, it probably would not necessarily be a valid broadcast address either. Not IP, but if it was a MAC address, it would be a valid MAC broadcast address. But so, because this is only 4 bytes wide, this little diagram right here is showing basically that we have 2 rows. And so there's our source address. And if we were to copy that again, there's our destination. Destination is usually abbreviated by DST, and source is usually abbreviated by SRC. Those are common. Okay. We went through all this last time. Oh, we didn't get the routing. Okay.
We briefly touched on routing tables when we were examining multitask.
Okay. So, let's jump into that real quick. How a host routes. So remember I said last time that the switch does a lot more. The switch is intelligent, relatively intelligent, and it has things that it does. It has services that it runs, and the router just kind of makes decisions about where to put packets on the wire and how to maybe override a packet header. Good morning. So the routers don't make all that many decisions as far as the depth of them. They're fairly simple decisions, but they can find themselves doing a lot of work when, for instance, when things are going wrong on the network, or there are errors and the routing table when it doesn't know how to make the right decisions. But here's what happens. So packets are created at the source. Okay. So, and that is, we talked about which, when we looking at the switch yesterday, we were really asking the question of which one of the, when the switch receives the packet, right, that was a real, concern from a couple people, is who's the sender and who's the recipient, right? And in the case that I take a packet, and it gets received on a switch, then the switch becomes essentially, if that packet gets broadcast out, the host that created the packet still becomes the source of the packet. But we can actually put that, this is after layer 2. So we've already stripped the layer 2 header away. All the layer 2 information doesn't matter. What's inside is still that broadcast packet. Okay. And this is an interesting thing. Each host device creates their own routing table. All right.
Thank you.
So I want to show you the routing table. You can find your own routing table. And Windows has a couple of different things that it uses. We've already looked at the ARP table. And the ARP table is that address resolution protocol table that maps IPs to MAC addresses. Okay. We'll learn about ARP in a little bit. But you also have a route table. And so what I can do in Windows is I can show internal routing table. And so this is the way that the host, in this case, the computer that I'm on as the host, begin to make decisions about where to send packet. And what gateway to use to do that. So the basics of that routing table is that I'm going to look for a network destination. I know what the network number is of my packet, and I'm going to look for that network destination in this list. When I find it, I'm going to know what gateway to use to address that device. I'm going to know what interface number to use. The gateway, it could be a default gateway. If I have a packet that is destined for any network that's not on this list, I'm going to use a default gateway. Okay. If I have a packet that's destined for any of these other networks right here, which could very well be true, I'm going to use the gateway that's specified for that particular network. So that's how we route, because we can have multiple networks on any particular interface or in the system itself. A lot of this stuff right here is because I have a lot of virtual network adapters. I have various virtual machines that have network adapters set up. You may or may not have all of these addresses on your PC.
See quite a few addresses too. I see the default. I see the basically the gateway of last resort, as Cisco calls it, at the very top of this particular system routing table.
Right. So,
And then
like you said, that's the gateway of last resort.
and then I just
It's
see
so dramatic sounding.
something like
It's so dramatic sounding. Gateway of last resort. It's like, ooh,
well, I mean, it's technically accurate because if the L3 information packet doesn't match anything else in the routing table, then the last resort before dropping the packet is to send it to the default gateway and see if it goes anymore, or if it gets returned, or you get an ICMP message, or actually it's routing, or if it just gets dropped into oblivion.
But it sounds like a tunnel of zombies or something. We're gonna send the packet down a tunnel of zombies. We're gonna eat your brains, faggot.
And I just see a bunch of stuff which means it's either local host or link local broadcast.
So all of these, and so what? Someone tell me what these addresses are right here. We talked about these. Desmond, what you got? The what? The ones that I've highlighted right here. No, these are certain class of IP addresses we talked about in the past. We were looking at different types of, maybe we didn't talk about. I don't think we, okay. So I'm getting my layer 2 mixed up. We talked about a type of address called multicast.
Are those multicast IPv4 addresses?
These are multicast IPv4 addresses, yes. And so, yeah, let me show you the ARP table, because here's where we were. We were talking about the layer 2 addresses that start with 01005E as multicast addresses. And so when you look over there at the interface address, it's at 224.
Isn't it a 224? Isn't the complete address of 224.0.0.0 with the CIDR suffix of 8?
I mean, it depends on what you're wanting to do. Some multicast addresses aren't that large, but yeah, that's the whole block. That would be called a super block. But yeah, that's the whole block of possible multicast addresses with the /8. But yeah, these are multicast layer 2 addresses right here, and they map to multicast layer 4 addresses right there.
And you said that whenever the destination MAC address is 01005E, it gets flooded out all switch ports except the one that it came in on.
Yes.
And then it's up to every host on the receiving end to de-encapsulate the L2 headers and then to read the L3 headers and determine whether it should process that packet or not based on the destination multicast address.
Yeah, so what it will do is it will de-encapsulate the packet, and it will figure out whether it is a subscriber to that particular type of traffic. And if it is, it will do something with the packet.
Otherwise, it just gets
dropped. Yeah. So a host can send packets to the following devices itself. Okay, and itself is 127.0.0.1. This is a special IPv4 address. It's called a local loopback. So anytime you want to reference a host's own IP address, that is the special IP address we use, 127.0.0.1. And that comes into play actually surprisingly very often when you're wanting to route services and do certain things and communicate with computers. Testing happens with this address. So you definitely want to memorize that address if you don't already know. There's a fun little meme out there.
It's like, what's your IP address so I can hack you?
No better place than 127.0.0.1. No better place like.
You just reminded me of one of the funniest IRC log excerpts that I have ever seen. This person had like a super flaky network connection, and they were getting bounced off of IRC like crazy. And they got real mad because they thought someone was hacking. So he asked the channel, what's your IP address so I can hack you? And someone printed out 127.0.0.1. And what he ended up doing is he had some tools on his computer. The first thing he did, he turned his own computer off. So then he got back in the channel and said, your firewall bounce might turn off, so go back to me. And then the other guy faked turning off his firewall. And then the other guy just wiped it. And then the other guy just wiped his own system without realizing it.
So there's no place like
Oh,
home.
okay.
And so when you think about that, you think about there's no place like home. I hope that you will always think 127.0.0.1. And that is just maybe that's something that you just practice, but it is something that every technician that has been in the field for even a couple of months probably knows and understands that line. There's no place like home. Okay? And that means me. All right. So when I'm thinking about myself, 127.0.0.1.
I've actually used that address before whenever I'm testing services and whatnot.
Yes.
I'd say I'll fire up a game server and I want to connect to it. So I'll configure the game server listen only on localhost because I don't want any traffic to or from that server being routable over outside of the physical system. And then I'll take my game client and I'll point it to localhost and it'll connect.
Yeah. So anytime you have any type of server that's running on your computer, you can get to it by addressing your packet to that IP address. This is called the local loopback address. Okay, local loopback. That means that the interface sees the packet, the TCP/IP stack puts it together, creates it, it goes onto the network, and it never actually exits the interface, but it does go through the TCP/IP stack and back up the TCP/IP stack. So that is a way to test your network stack to make sure that it is functioning.
And if you can't get a basic ICMP ping packet through on the local interface, everything up the entire TCP/IP stack needs to be closely examined.
Right. That's right. So this ensures that my computer can read IP addresses and understand them.
It's like a basic literacy test in networks.
And so when we look at what is local hosts are things that are on the same LAN. Remote are things that are on different LANs. So when local and remote, these are other terms that oftentimes are relative terms. So we have to continually switch our definition of what is the definition of local and remote stays the same, but the field that touches changes. So here's an example. If I have this router right here, R1, what is local to that router?
Itself.
You say it was low or something?
Yeah.
Wouldn't it be like, if there was something local to it, would it be like next to it? Like, local,
Yeah, it's on, so something that's on the same network that it's on.
the host.
So what we have in this particular picture is we have two networks. One is a remote network. One is a local one. So this particular server is, because they have a cloud in this picture, we don't really know where this server is located. Okay. It's sitting over there. It could be in Japan. It could be in Malaysia. It could be in Austin. Okay. Currently, the thing that is remote to this router is this server right here. We call it remote, but we don't really know where it is. But what we do know is that it is not on the network that we're on.
So is the remote host feeding the cloud? Or is it going straight to the route?
So yeah, the remote, so what's happening in this picture is the packet from the remote host is going through router after router after router after router, and eventually it gets to the router that's connected to my router. Eventually it gets one hop north, so to speak, of this router. And then the next hop is the router that is on my network. So it could be 12 hops, 25 hops, or 3. Right? We don't know how many it is. But it's just remote and it's out there. And so this whole system gets replicated over and over and over because there's routers in the way. But what is local to this router? We say that something's local.
Would it be a switch in the computers?
Yes, the switch in computers. So when we say that it's local, the network that is local is 192.168.10.0. That's the network that's local. And we put that thing on the end of it, /24. That's the CIDR notation. It's also called the suffix. And that tells us how big the network is. It tells us how big it is. And when I say big, I don't really mean a physical big. I'm not talking about its geographic width, breadth, or depth. I'm talking about big in terms of the number of possible hosts that could be on that network.
So like the address, it's like the maximum addressable space within that network.
Yes, so in this particular case, that 24 is going to denote that of my 32-bit IP address, 24 bits signify the network side of the equation, and the other 8 bits signify the host portion of the equation. So whenever you see those numbers, that's telling you how big the network side is.
So in which case, that only leaves a last octet open for host bits.
Say again?
In which case, that only leaves the last octet open for host bits.
That's correct. Yeah, that only leaves the last octet open for host. So those last 8 bits.
And you can split and you can split the boundary between network and host bits across octet.
That's correct. Yeah,
Say in
that's-
case
That's not where we're at yet, but yeah, that's true.
that's getting into subnet, right?
Okay. So, now like this, let's see, the source address, the source device determines whether the destination is local or remote. So it's my source that determines whether the destination is local or remote, okay? So if I have a packet that originates right here at PC2 or PC2, and I am sending a packet, and let's say that PC2, we'll just make another notepad. So here's what this means. If I have a network, now this means that what I can do is I can number that network starting with a host of 1, and my next host could be 2, and my next host could be 3, 4, and 5, and 6, and 7, and 8, all the way to 254. Okay, I could have that many computers, devices, things on my network. And what would happen is all of those devices, things, or equipment would be local to one another. They would be local. So if I had a computer, PC1, and its address is 192.168.10.2, and PC2 is 192.168.10.3.
It's not the 20.
Okay. If PC2 sent a packet to PC3, or sorry, if PC1 sent a packet to PC2, then the source address is going to be this address, and the destination is going to be that. And so they're local to one another. We could say that the destination address 192.168.10.3 is local to the source address 192.168.10.2. Yeah, William.
So if PC1 did not know the MAC address of PC2, it would first perform an ARC lookup to get the MAC address of PC2, and then it would put that in the destination field of the layer 2 header, and in the upstream switch would route it to PC2.
Yeah, that's what would happen. That ARP request would allow it to create the layer 2 packet. But yeah, that's exactly what would happen. But just talking about addresses right now. Okay, I'm trying to establish the local and remote relationship. So does everybody have any questions about how we determine what is local and what is remote?
I got a question about the local type.
Sure.
I kind of missed the local part. You said, so would it be local because of the numbers?
Yes. Yes, that's exactly right. So it's local because my network portion of the address, which is right here, are the same. Because we're at the IP layer, okay, we're beyond layer 2 right here. We're not dealing with layer 2, so we don't have to worry about the segment. Okay, so I'm not talking about the broadcast domain at this point. I'm talking about only the network layer. We're going to assume that the packet was delivered properly to where it needs to go. And now we're looking at the IP address of the packet. And yes, it's because those numbers are the same. They match. So this right here tells us how many bits we have to match. So what I can see is that I would match the first 8, the second 8, and the third 8. So that's 24 bits that match.
Yeah, the bid is one number, right?
A bit is 1/8 of a number. So that 192 looks like that. I got one too many zeros.
No, I'm like, so you say it has the, okay, so whatever number, okay, so like the slash 24, whatever number that is, that's how many it has to match. So what do you mean like it has to match the bids, like how many on the network, like?
Yeah, so let's carry this out a little bit farther. So let's say that my PC1 created a packet. And PC1's IP address, if I carried it out, looks like this. That should be right. So PC2 is going to create its packet, and PC1 is going to create a packet destined for PC2. And so what it will do is it will say, okay, how do I get to PC2? Its address is 192.168.10.3. And it's gonna address its packet to PC2. Now, what the network card will do is it will look for basically it knows when it matches the packets, it knows that if I am in this, if my address are these series of bits, then any packet that comes to me that has the same series of bits is a local address. And so when we look at it like this, we can visually see see that these things match. So in this case, the first 24 bits, you see it? Okay, they match. So my network card goes, oh, hello neighbor, you're local to me. That's it. Okay, cool. That's what happens. And so the differences now only become, the differences in the host are these bits right here. Okay. And I think I did that wrong. I think this is number 3. And this is number 2. Okay. Yeah, 2, 3. Okay. Yeah. So anyway, that's what our source and destination addresses look like in the packet. But what we do is we just shorten those down to their hexadecimal numbers. And so we'll see a sequence of hexadecimal bits. Does anybody want to try and convert that?
Did you, it's the same number, right?
Huh? Yeah, what is it in hex?
What did you just convert it from? You converted it from, in the IP address, what was that?
It was this right here, 192.168.
Or what would that be? Is that hex again?
This is binary.
No, the IP address. Would that be just decimal?
That's decimal, yeah.
Okay, all
Yeah, so that's the decimal side. This is the hexadecimal side. And then binary. Let's take that and make it into hex real quick. It won't take long. Remember what I said that when we first started talking about it, we could take this and we could cut it into two pieces? So now all we have to do is remember our 0 to F.
right.
So if this is the 8 and this is the 4, 8 plus 4 is 12. And then what's 12?
C.
Yeah, see. And then we have 0. And what's this one? So what we can do is we can remember that this is the 8th place, the 4th place, 2's place. Okay. 8 plus 4 plus 2. 14. What's 14 in hex? E. Then we got a 0, right? Another 0. What's this one? 10. And what 10 in hex? A. Not control A, which is what I did. All right, then we got a 0. What's here? 2. Yeah, 2. So we just took an IP address and we converted it into 4 bytes. There it is. That's what our network cards do. That's what our web browsers do. That's what our Wireshark does. We got hex here. We got binary here. Bootbar. We're just going to say B, H. And here's our D for decimal. Okay. Okay. Same thing applies. If I address a packet, I'm going to see C0, E0, 0A. That is the network portion of the IP address. So let's see, default gateway, remote traffic. So this is how the host figures out, is it local or remote? If I'm sending an address, so let me show you this. Okay, so let's just say, this is, I don't know if you guys saw in my Discord, at one point I was talking to some people and I said, computers are dumb. Really, really, really dumb.
They just do what you tell them to do.
Yes, they do what you tell them to do, and they're otherwise very, very dumb. And so I want you guys to always remember that. If there's a lot of things that I'm going to tell you that hopefully you'll carry with you, the one thing that I really want you to remember is that you are smart. Computers are dumb. Okay, you guys know the answer. We have to exert our dominance over the computer. Don't let them get one up on you. Okay.
If you mistype something while you're configuring it, it will gladly let you mistype it all day.
So I want to show you how things work behind the curtain, because what we're doing is we're uncovering. This is like going to Oz and seeing how the wizards do things. Okay.
Before you start, I got a question.
Sure.
So say you can this or CLI, you probably already know. Say you going down the road or whatever and you make a error. Like, would you type over it or would you start completely over?
Oh, okay. So, good question. So let's just say it. I'm going to go and I'm going to run a program called NS lookup. That's the right way I would do it. But so you're saying what would happen if I wrote NS lookout instead? It was wrong, right? So if I caught it before I pressed enter, I would just backspace it and put in the right thing. But if I didn't catch it, and I was like, oh man, NS lookout, what's that? Okay, here's a couple things I could do. And I didn't want to go, maybe I had a command that was like a really long involved command, and I had a switch that was a server, and then I had some other blah, 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 right? Right, okay.
Oh, so it just wouldn't go through.
It tried, right? It gave me a whole bunch of stuff. So it didn't know what ALASFD whatever was, right? It tried. So what I could do is I could press the up arrow on my keyboard, and it puts it all back there for me. And you can do it in your switches and routers and whatnot. And now I can backspace that out. I can even use my left and right arrow keys and the backspace key and get right where I want it to be. So I could go over here and go, oh, I didn't mean that. I meant to put a space right here and another dash. And they're here too, right? So I can edit my command line. And so what I'm doing here is I'll put that in there. Okay. So what I'm doing is I'm pressing up arrow, and then I can backspace out everything and type it in again, or I can do left and right arrows to get in there and change stuff. That's the trick, right? If people are like, you're like, how did they do that so fast, right? It's when you mess up, you can go back. Now, if I'm in Windows, that is what I get. If I'm in an SSH session, sometimes my keys don't always want to work the same way. And so maybe I press that left arrow key and I get some gobbledygook, right? Now, if I get a control sequence, when I press that left arrow key, I usually got to do a couple things. Like sometimes it'll give me this stuff, like I'll press my left arrow key and it'll do this kind of a, it's called an ASCII control sequence that will happen. All right, it'll just appear when I press my arrow key. Sometimes I can press a modifier like control and an arrow, and it will allow that arrow to go over the connection properly and go in. Other times I'm stuck, I just got a backspace. So, but yeah. Okay, so we're gonna use NS lookup, and we're gonna, because what we did was we typed in google.com into our web browser. Okay? And the web browser says, well, I don't know who google.com is. I've got to go figure it out. And so it does a DNS query, and it comes back with a list of IP addresses. Now, if I'm in IPv6, and I'm using IPv6 as my network, I'm going to use this address first. If I'm IPv4, I'm going to use this one. It's the first one that was returned. That's how we know which one's going to be used. It's the first one. If that one, and the reason why I have more is because if that one doesn't work, I can immediately go to the second one and try that one. So if there's a short timeout, and I'll end up cycling through all of these IP addresses to try and get to Google. But so this tells me the address that I'm going to use to send a packet to Google. All right, so we'll go back to this demonstration right here, and we have PC1. My address is 192.168.10.2. That's my source. My destination is Google 142.251.116.101. All right. Yeah, 142. Thanks. 142.251.116.101. So these numbers look different because the network card is going to say, okay, do these 24 bits match? The answer is immediately no. They do not match. So I do this. I get an answer that is not in the affirmative. I immediately know that that packet goes somewhere else. So where does it go? The PC looks at the routing table, and it looks up all these networks, and it knows that it's not in the list here, okay? It's basically in the other list. It's going on the gateway of last resort. So now that I know that this is the location of where it needs to go, I can do this. I can look up that address in the ARP table. There it is. And I know that I can create a packet destined for that address, and it will be delivered to the gateway. That happens every time. If I had to do this by hand, I would hate computers. with none. So look at this. So guess what? So if I got that IP address and I want to look at Google, I can put this IP address in here. I don't have to put that google.com in there. That proves to me that my browser is actually doing a DNS lookup and it works.
Didn't it actually do a reverse DNS lookup? Because instead of going from host name to IP address, from IP address to host name or domain name, I should say.
No, it doesn't do a reverse lookup. It does a forward lookup. And so it goes and looks up the query section in the DNS packet is google.com. So that's a forward lookup. If my query section was the IP address, it would be a reverse lookup, but it doesn't do that. So we'll do NS lookup google.com and we'll just do this. I'll go to each one of these.
I remember doing something like that a long time ago on Minecraft. Like Minecraft, like works with IP stuff like that and routers.
Yeah,
Yeah.
to like a different server.
Like one time I tried to make a server and like it made me do all the IP. I had to buy like a router and stuff like that.
Yeah, you had all these around, you port forwarding that stuff, so you had to make the port all the way to the network and whatnot.
And I was just a web and I ain't gonna do that. I did. But
So there's my address. Now, if I was running IPv6, which I'm not, I could also do the very same thing here. And I would get to Google, but
You just need to be doing a search instead.
yeah, I'm running V4 single stack. Okay. So questions? Anybody? Yeah.
So, and the reason why it instead kicked out to a search on the default on the default search engine instead of actually going to the IPv6 address is because it tried to send it down the link local address, which obviously doesn't work. So
Right.
it got nothing valid back from that, so it just
Right.
translated it into a search and went from there.
Yeah, it just that's exactly what happened. It took it literally like I was typing in that
So
as the domain name.
I don't know why IPv6 isn't as common as it is.
Okay, so remote and local. It's now here's another. Let's just look at this here. So here's one thing I want you to know about this is that while we match these, while these numbers signify, the decimal numbers signify the source address, and that's how it determines local and remote, we have to remember that it's really these bits that it uses to make that determination. That's what's really happening. So we'll start looking at network masks and how we determine what's the host and what is the network here pretty quickly. But here's an idea of a default gateway. So when you have a default gateway, it has to have an IP address that's in the same range. Basically, that means that the IP address of the interface on the router has to be local to the network that's attached to it. Okay. If it doesn't have a default gateway or bad gateway, its traffic will not be able to leave the LAN. So if I have a router plugged in and that interface has an interesting IP address that's not local to the network, it's on, it won't work. So let me show you this idea real quick. be the last thing we do today. Okay. Here's my PC 192.168.10.2. Here's my router. We're just going to plug it right into a router, R1. And I'm going to say that the IP address I'm going to put on that router's interface is 10.2.3.2. Okay. And I just did whatever I wanted. Some days it just feels good to do that. The Monday, why not? We'll just do whatever we want. Okay. So what would happen is that I'm trying to forward this packet onto it's an external packet, and I want to get it onto my default gateway. My interface is going to look at the source address of the packet, and it's going to say, this is a remote network. I can't send this. I can't handle this packet because my network is 10.2.3.0. Right? I can't handle a packet that's coming from 192.168. 10.0. I have no routing table in my router for that. Can't do it. Drop. So it's not going to work. Yeah.
So I'm guessing everything to do with IP addresses and whatnot is up at layer 3. Right. So while layer 2 might forward the packet, while layer 2 might do an ARP request and get the packet forwarded on to router 1. Router 1's L3 portion of the TCP/IP. Router 1's IP subsystem is going to be like, I don't know what this is, and it's just going to drop into the void.
Yeah, we can get the packet there, layer 2, right? We're stripping the layer 2 header off. We have no idea what it is. We don't get to look at it and reference it anymore. It doesn't exist. All we have is the source address. And so we're looking for what we need is we need our router interface to be on the same network. Now, convention says that I number that router interface as .1. I don't have to. I'm an engineer. I can do whatever I want. Okay. Now, the question is whether that's the right thing to do or the wrong thing to do. But I could number this thing any number I want to. I can make it 100 if I want. It just has to be a host address on the network. Right? Convention tells me that I go ahead and make it 1. Make it easy. I want to do things easy.
Because it's usually the first device on that subnet.
Yeah. That's what convention says. Now, Dan Darden's rules, I'm the engineer, I can do what I want. It's not always the best rule to live by. You want to go by convention, okay?
You could put it right smack in the middle of the subnet.
You could, you sure could. So it's important to know that because that demonstrates that you know how this works. A router, it is just like any other host on the network.
It just has a special.
The issue is that when it receives a packet destined for, okay, that's the key word, destined for a remote host, it looks up that address in the routing table and forwards the packet. Right? That's the difference.
So on a router, you basically do the same thing. Well, not really. That's it, right?
Are you trying to ask if it does the same thing the switch does?
Yeah, like program, like you putting up commands. So
You do in a way. There is a very similar program command set between a router and a switch. What we're doing when we program a router is we turn on different services that allow it to route. So traditionally, a router was a very slow device. It was like, you know how you get in the car, right? And you're driving down the road and you get behind a tractor and you're like, "Dad gummit, why won't this guy go any faster?"
Yeah.
Well, that's kind of what it was like in the olden days when we had a router that was routing packets for a network and we had a switch that was really fast. And so there wasn't as much traffic being put onto the network on the external network as there is today. Routers have gotten really, really fast at what they do, but they weren't always that way. They were slow. And so, yeah, it does the same thing as the switch in the sense that it interprets the packets and de-encapsulates them. But the router does one other thing the switch can't do. It decides whether or not it can forward the packet off the network.
But what I was saying too is like you would have to go into the router and set that.
I mean, you got to turn routing on.
Okay.
Yeah. And so the question becomes, how do I turn routing on? And what routing protocol do I use? And that's the prerogative of the network engineer. I get to pick that. And I pick it based on lots of different things that exist in the environment. I could do a very simple routing, which is a static route. That means that every single packet that you receive, you send one hop over. Or I could do a very complex route, which would be like OSPF routing, or an EIGRP routing table, or IGP. Those are a little more sophisticated.
Like open source path first, enhanced internal gateway routing protocol, internal gateway protocol, and whatnot.
Yeah, whatever you want to do.
And those are within autonomous system networks, right?
Yeah, inside the autonomous system, right? So once we get past the AS, we have different routing protocols,
Such as AGP.
BGP, right?
Border gateway.
And that's pretty much it. Yeah. Okay. So, going back into routing, just the simple version of it. Now, Cisco will abbreviate this default gateway DGW. So when you see that default gateway, is what that means. I have never seen that in real life. DGW, that's just not an acronym we use in real life. I think they're using it to avoid having to write that out every time. I mean, but that's not really, you won't find this in documentation, I don't think. You will see RS, router solicitation. And that is a message that IPv6 sends out. And a default gateway is a static route, which will be a last resort route in the routing table. So that static route is basically, another way to say that is a next hop. So the static route contained a next hop address, or it just contains an interface. And so the advantages of having an interface that is a point-to-point or a serial interface is that I know and I have a guarantee that everything I put on that serial interface comes out the other side. All right, so I don't even have to have an address in my router. Not required.
You just need to tell it the MAC address of the interface.
You don't even need that. You just need the interface name. You just need to tell it what wire to send it on.
Like slip 0 or something.
Like serial 001. That's a valid interface. So here's our routing table. Oh, we're done. We're out of time. So sorry, guys. We'll continue. Read the rest of this module 8 tonight. Read about routing tables. And we'll see you tomorrow.
All right.